This is the Team 3 presentation, analyzing the first week of refrigeration tests. Chillers Inc. has contracted Burdell Inc. to evaluate their new cooling system. The cooling system utilizes a vortex tube and air as the working fluid to cool the load. In order to accurately characterize the system, Burdell Inc. will first measure temperatures, pressures, and mass flow rates at important steps in the refrigeration system. These measurements will provide the vortex input and output pressure, but will also be used to characterize the heat and energy transfer of an aluminum block used at the testing load. The ability to cool the aluminum block will determine the effectiveness of the refrigeration system. In the analysis, the sensor offsets for each state need to be determined. T ambient measures the ambient temperature of the room, verified against a local thermometer. T1 is the initial compressed air temperature. T2 is the air after the air-to-air heat exchanger. T3 is the air after passing through the accumulator tank. And finally, the air splits at junction 4 into hot and cold air after passing through the vortex tube. 4H is the hot air, while 4C is the cold air exiting the tube. The cold air continues through the load and finally exits at station 5. The load is the aluminum block, and the cold air is used to cool the block, accomplishing the refrigeration system. Initial testing will focus on the steady state response of the system at each key temperature point. Secondary testing conducted after this presentation will perform transient analysis of the system, using air from the compressor and the building to cool the system.
All of the sensor values output from the system needs to be converted to corrected units. Pressure was recorded in psi, which needs to be converted to newtons per meter squared. Temperature was recorded in Fahrenheit, which needs to be converted to kelvins, and volumetric flow rate needs to be converted to mass flow rate, which is in kilograms per second. This table shows all the conversion equations applied. To ensure proper readings from the sensor of the system, the initial offsets are calculated. The temperature, pressure, and mass flow rates at each station are recorded with the system completely shut off. Ideally, each sensor would measure its ambient pressure, temperature, and zero mass flow rate. The table shown below signifies the difference between the measured values and the expected ideal values. These two values are subtracted from all future results to measure the true conditions at each station. Two tables are shown since a separate experiment was conducted for the 2.5 volts case, which required different offset values. The team then proceeded to measure each station in the system at steady state. Since the motor and compressor combined together create pressurized air, in order to control the pressure of the system, the linear relationship between input voltage and pressure must be determined. This linear relationship will be critical to transient tests in the future when the compressor must be kept at the specific pressure of 40 psi. To determine the relationship of the vortex tube's temperature outputs given pressure inputs, a linear fit between input pressure and the mass flow rates at cold and hot station 4 is created, which is displayed. The linear relationship equation shown characterizes this behavior, but theoretically, a nonlinear fit may be the better representation as, by inspection, the data points follow a parabolic trend. To determine the output relationship of the vortex tube's mass flow rate given pressure inputs, the linear fit between pressure and mass flow rate at cold and hot station 4 is created, which is also displayed on this slide. The linear relationship equation shown characterizes this behavior, and while the mass flow rates increase in both cases, theoretically, a nonlinear fit may be the better representation due to, again, the parabolic nature of the trajectory. Now the team analyzes system components given steady-state data collected.
Ideally, the heat exchanger and accumulator is able to attenuate the pressurized air input's temperature to T ambient. The heat exchanger in lab was experimentally able to attenuate pressurized air inputs to within 0.28% of T ambient, while keeping the pressure constant. The heat exchanger is a critical step to cool T3 before the vortex tube. At higher input T3 temperatures, it was shown that the vortex tube is less effective at separating the flows into hot and cold. The nonlinear nature of the cold flow temperature versus pressure input illustrates this. At higher pressures, and thus higher T3, the vortex tube cannot produce equivalently colder streams for each increase in pressure as it did at lower pressures. As a result, it is critical for T3 to be made as cold as possible by the heat exchanger before entering the vortex tube for the coldest possible output flows. Ideally, the compressor is able to reach higher temperatures whenever the motor is applied with more voltage. However, when characterizing the relationship between T1 and input voltage, the relationship is not linear, and with increased voltage, T1 will flatten out and not achieve higher temperature values. This demonstrates the limited capabilities of the compressor to achieve high temperatures. In an ideal reverse Brayton cycle system, there is no pressure drop across the heat exchange with the load, between stations 4C and 5. However, the system used is not ideal, and the air experiences a pressure drop as it cools the aluminum block. This is due to frictional pressure losses as the air flows through the exchanger and demonstrates the losses of a real system. These losses resulted in a 57% pressure drop across the load as the refrigeration system cooled the load. Now the team is able to build a steady state model.
After assuming that the theoretical insulation thermal conductivity is 0.33 watts over meters Kelvin, and taking the internal and thickness measurements, the equation on the bottom left is used to find the theoretical Q dot ambient. Solving for the experimental insulation thermal resistance, data can be plugged into the equation in the bottom right. Using the measurements mentioned before, an experimental insulation thermal conductivity can be solved for and compared to a theoretical value. This table holds the values for the aforementioned process. Starting with the left side, it can be seen that there's a large discrepancy between theoretical and experimental insulation thermal resistance. The only thing that is being changed between the two is the insulation thermal conductivity, because the internal measurements and depth do not vary. The insulation thermal resistance is much lower than expected, and thermal conductivity is much higher. This can be attributed to assumptions made in the model that are not accurate. The styrofoam block that was used was taped together with gaps along the seams, leading to losses in energy. In addition, the thermocouples used to measure temperatures, especially the one for load, were not placed in the center of the load as assumed by the model. They were placed on the edge, leading to lower temperature values. This led to a higher amount of energy lost, as seen in the higher values for experimental. Moving on to uncertainty, shown on the screen is the formula used to calculate uncertainty for the energy transferred to the cold air. All of the partials having to do with mass flow rate of the cold side, T5, and T4C can be seen in the second row. The 4 rows below hold the formulas for the uncertainty of the equipment, the flow meters, and the thermocouple. It can be noted that another analysis was done on the second to last row to turn the Fahrenheit uncertainty to Kelvin uncertainty. The uncertainty analysis was also completed for the energy entering the system from the environment. There's only one partial in this case, which has to do with T load, and the equipment uncertainty was found from the previous slide. As seen from the first two data columns, the uncertainty from the energy transferred to the cold air is much higher than the uncertainty of the energy entering the system from the environment. The difference in the energy transferred to the cold air and the energy entering the system from the environment is much higher than those two uncertainties added together, and that is because the energy leaving the load cannot be assumed to be zero. The temperature of the load changes over time and causes Q dot air and Q dot ambient to not be equal to each other. Because the last slide contained only theoretical values, an uncertainty analysis can be done on the experimental insulation thermal resistance. This equation shows all the partials needed to calculate the uncertainty, most of which were previously shown. Even with the uncertainty, the experimental value does not fall within theoretical. This can be attributed again to the modeling errors mentioned before. There's assumed to be no gradient of temperature, and throughout the experiment, average values were taken at steady state, which does not account for outliers. Furthermore, the system assumes a point source of temperature, which is not true because the system components are not point masses. Adding to this fact that the measurement is on top of the source, there's bound to be error.
The analysis that needs to be continued will include the transient analysis on the system, which tests the ability of the refrigeration system to reach steady state quickly. The team will use the building air supply to provide the system with excessively high pressure, 80 psi, while the compressor will supply 40 psi in a separate experiment. From the steady state analysis conducted for this presentation, it is hypothesized that the higher pressure air will cool the load more quickly, and further, between experiments with the separate airflows, it is critical to return all sensors to ambient pressures and temperatures to ensure accurate time to reach steady state. Here are the references that we used throughout the presentation. Thank you for watching the Team 3 presentation.